Okay, so hi everyone, and welcome back to an exciting afternoon session we have. I just have two quick announcements to make before starting. So firstly, tomorrow we'll be starting at a slightly earlier time, so tomorrow we'll be starting at 8:30 instead. We've been running into some AV issues, so just a request for all of tomorrow's speakers to also just double check their slides with the AV people and see that everything displays correctly. So we have a very exciting afternoon session, and it's going to be on deep learning in science. And I'm very excited to have our first speaker, Regina Barzilay from MIT, and I'll leave it to her.
Thank you. Thank you. So today I will talk about great opportunities that we have to change chemistry with deep learning. And my background, does it work now? No? See, it doesn't work? Isn't it funny? Okay. Let's just use it manual. So to tell you the truth, that I'm a natural language processing person myself, and 3 years ago I was approached by somebody at MIT who was submitting a grant to DARPA about using deep learning for chemistry, and I thought, why not? I didn't even know what retrosynthesis meant at the time when we started this proposal together. And within 3 years, this became one of the kind of major part of my research activities, and now we build a lot of tools that are used in pharmaceutical companies, and we are running pharma consortium where we are trying to understand, what is needed and how to develop appropriate algorithms. And I will talk most of my talk about kind of intellectual appeal of using learning in chemistry, but I just want to tell you, what is my personal motivation is really to do better in drug development. And you see that the price of the drug development increases, and this is really not surprising, because if you're looking at the space of molecules that you have out there, it's huge combinatorial space. And the way today the drugs are developed, you just do a lot of high throughput screening, and through this huge space with some human intuition you identify the lead and go to further testing. So the questions that we have, can we actually use the predictive power of machine learning to help us? And if you're thinking about chemistry, most of the crucial chemical question, actually prediction questions. So I would give you some examples. Property predictions, when you're trying to predict either bioactivity or whether the molecule is soluble or toxic or so on. The second one, what most of you have done, introductory chemistry classes, when you are given, different reactants and you try to predict what will be the outcome of the reaction. The questions related to modeling biological and chemical properties. And finally, the one that in the very bottom of my slide is a task which is kind of really the art of chemistry. It's coming up with the molecules which later will become the treatments and the drugs. And I just want to say, back to our discussion about humans and human scientists versus machine, what I kind of brought up in the early conversation during the panel. So when we built one of our first system was trying to learn how to predict the outcome of reactions. And this is exactly the task. Well, this is exactly the task. And we got some number that we put in our NIP submission. And I was really curious, how well do we do relatively to humans? And the way we did it, we collected 80 reactions and gave them to postdocs in chemical engineering and organic chemistry at MIT. So I will show you how did it work. So our model predicted 69 reactions correctly. The average of humans was 54. There was only one human who outperformed the machine, and this was the head of our chemistry department, Professor Tim Jemison. And I don't want you to take conclusion out of this talk that, postdocs that you have in your university or in your company in chemistry are much better. It just tells you that the task is really, really challenging, and the models that was developed within few months can already do competitively with humans. But what I want to talk to you about today in terms of science is that when we are moving to a new area, and chemistry is an area which is really, really unexplored, when we compare it to, for instance, natural language processing or computer vision, is how do we design those models? And one option is to take all this great machinery that, previous speakers were describing and saying, isn't it great that now we can do our, game playing using the same algorithm that Chris was describing for machine translation. So one option is just to take this machinery and just apply. And another option to think how we can take chemical structure and do a better job. And I will tell you where we're standing in this area. So I will talk as an example of about 2 questions, since the talk is relatively short. One is property prediction. And the reason this task is interesting, because this is a place where computational chemists have been working for decades. Even before deep learning systems came, when you have a molecule, you need to predict the properties of molecule. The last one, this lead optimization, this is a task that is very much not automated. As far as I know, all the molecules that have been developed, they were developed, by the brilliance of chemists or biologists who designed them. So let's start with the first one. So the first one is, again, property prediction. You are given a training set where you have your molecules and you have some property, let's say toxicity, and you are trying to predict whether a new molecule will have this property. Traditionally, people did it in the following way. They took the molecule, which is a graph, and translated it into something which is called fingerprint. In our language, we would call it feature vector. You just record different type of substructures that you have. And, our collaborators in pharmaceutical company have their own kind of hidden feature representation, which they think are really, really great. So the first question that we ask is, can you actually learn this representation instead of using human intuition how to represent molecules? And I'm sure all of you are thinking, of course, we can do it. We can take the molecule and do graph convolutions on the molecules. Let me just briefly describe how it may be happening. You start with every atom have its own vector where you record important properties of this atom, and then all the atoms start kind of exchanging messages. So I am getting information from my neighboring atoms, put it together based on how I predict the property, and I do the update. And originally, I would have information about myself alone, then I would have information about my neighbors, and slowly I will collect information about the whole graph. So this is a very simple idea, and again, following up what we discussed in the session where Chris Manning was showing to you words, we can similarly see chemical space, that if you look at these lambda representations and project it in 2D, that what I've done here, you would see there are a lot of molecules which are very close in terms of their chemical properties. They would be close, in 2D representation. So at any rate, we did very well. We tried all possible public benchmarks. We did great. And then I want to talk to you about the mystery of property prediction, okay? So at any rate, we did well, and I was like so happy. And I sent an email to companies, not an email, a blog. I sent a blog to all the companies which are in our consortium, say, guys, we're doing so great. And they always ask, how do you do comparatively to Stanford? I said, you see, we did even better than Stanford. We just did great. So you should take this tool and use it. And there was one company that was excited to use it. It was Amgen. So they took our tool and applied along with their own home-cooked tool, which use, human-engineered feature vector and use some very simple machine learning tool. And I was sure we're going to beat them a lot. And as you can see here, we actually didn't. We barely, we did slightly worse than them, but it was completely not what I would expect, and kind of state-of-the-art deep learning model. I was really confused. So I know that I'm taking like half a second from my time, but I want to ask you, can somebody here guess why it wasn't working? Why did it do so poorly? Exactly, exactly. This is exactly the point, that when we are creating our standard benchmark data sets, which are used by people like myself who actually never work in pharmaceutical company, what we do random split between training and testing. What actually happens in pharmaceutical companies, they do something else. This is what the situation with their test. You can measure how similar molecules are in terms of their scaffold. What happens, they do temporal progression of the molecules. So what you see in training is actually very much not what you're going to see in testing. And in order to perform well, you need somehow to generalize. And the reason that they did better or comparatively well was because they engineered very well their features. So when I saw this, it was like a disaster. I felt really terrible that we did poorly. So we worked very hard here. And we did a variety of tricks to make the performance up. So to make the story short, we are now doing better than them and many other companies with their homegrown fingerprints. We added variety of things. We did, Bayesian hyperparameter optimization. We did ensemble, did a lot of tricks. We managed to bring the performance to the acceptable level, both on public dataset and private datasets. Now you can say, am I happy? No, I'm not happy. Why I'm not happy? Because if you compare, we do better than the pharmaceutical companies. But if you look here at these arrow bars, you would see the arrow bars. This is experimental arrow bars. So can I really say that now you don't need to do any experiments and you can just use our model? Unfortunately, I cannot really say that, at least for some data sets. Of course, you can approximate better the empirical error by, what I mean by empirical error, because I do really high throughput screening, and not every time the same measurement come back. So that's what we compare. This is our upper line. And we can see for some sets we do well, for some we don't do well, and of course the more data you have, the closer you can get to the empirical error, but it's not what we want, it's not where we want to be. And when I'm thinking about what are the open questions here, you know, the way I solve this problem is like doing, you know, the standard kind of deep learning engineering tricks to make sure that it works and it generalizes better. What I would like to do, and we're looking at it, and I think there are other people in the community who are thinking about it, is actually the question, what is an adequate representation for molecules? First of all, you know, we may want to move from 2D to 3D, because molecules are actually 3D graphs. This whole graph drawing is something that human invented, because we know again that atoms, you know, are oscillating. It's not like a static picture. So maybe we need to have something much more dynamic, which brings us to the second question. How can we take, you know, underlying physics and use it as part of our model, so we don't plan the whole chemistry each time for every property and U? Can we infuse this knowledge into the models? So that's where we're here, and, you know, to the best of my knowledge, I didn't see really strong results in deep learning in this area would demonstrate to us the advantages of this knowledge, but I do think that this is a way to go. So now I want to move to another question, which is kind of this art question. How can you take the molecule and generate another molecule with better properties? So let's say you did your high throughput screening, you got something that has the right bioactivity. Now you need to modify it to make it soluble, to make it non-toxic, and so on and so forth. So can we do it fully automatically? So in terms of drawing, again, referring to Chris's talk, you know, you remember when we are learning the properties, we're actually translating this graph into the continuous vectors, correct? So what we want to do, we want to start in some place in this continuous space and then optimize it, get to the good point in space, and then generate the molecule. So you can think about it roughly as a translation process where you start in certain place, which is maybe promising but not great, and you improving and generating something better. And this is yet another picture. We want to be able to traverse our continuous space, and we believe it should be easier for us to optimize it because it's nice continuous space. And now I want to talk about, you know, reusing the tools. So again, we have great approaches that were developed in NLP for doing string-to-string translation. You start with English, you translate it to French, correct? So the first sort of people who tried to do it was to say, great, let's just take these methods and apply them. But molecular is a graph, so what we're going to do? Oh, in chemistry, we have something which is called smiles. You can take molecule and in some way linearize it into a string. And people tried it, so you linearize it, you optimize the property, generate new molecules. This approach worked very poorly, because when you do this translation, several bad things happen. First of all, we know that similar molecules may have very different smiles, so it's really hard to control for the smoothness of the space, and also this method is not guaranteed to generate valid molecules, smiles that you can translate into graphs. So here we actually, so the next idea would be to use what we again know from computer science, is to go from graph to graph. People again tried it. It's a problem because you would have a lot of intermediate steps, which are valid graphs but invalid molecules. It's hard to validate, and it also takes a lot of steps. So we got some inspiration here from chemistry. And the way that chemists look at the molecule is the same way as we look at the sentence and we see words. We don't see letters necessarily. And here the function of kind of this unit is called these function groups, which encoded meaningful chunks of the molecule. So pretty much you can take this molecule as a chemist and you would see all these different function groups. And there are very few function groups that will describe accurately, you know, the large, can describe accurately molecules. So what we've done, we translated this molecule into the trees, which make us feel closer to my core area, natural language processing. So now you have your molecule. You represent part of it would be the encoding of the tree. Another part is the encoding of the molecular graph. You do optimization, and you generate the graph and generate the molecules. So it worked pretty well. I would not bore you with numbers. But one thing that we've noticed, the whole presumption, and if you read that paper, you would see we wrote, we want to have space continuous. And that's what we believed when we submitted the paper. It worked well. But if you start actually more closely analyzing what the model is doing, you would see that the space is still not continuous enough. And how would you know? You take a property, which is a very simple property, and what you see, that if I'm starting with some molecule and I'm enabling myself to go very far, I can greatly optimize this property. But if I limit my radius in terms of molecular similarity, I would be unable to do so. And you can also demonstrate it by looking at how you cannot interpolate well in this space. So then we again came back to natural language processing and sort of the following idea, that the same way as in machine translation, where we did a lot of progress, we still can only do well machine translation if we have pairs of sentences. You have English and you have French, correct? So, and you learn this translation. This is a scenario under which today's deep learning models can do translation. So the thought that we had was, can you actually do the same for molecules? You can take a corpus of molecules where for each molecule you know the property, and you can create the pairs. You take two molecules which are close one to another. One is the original one, another one is with improved properties. And you are back to machine translation scenario. And the only thing that I wanted to say, what people in chemistry care, and I don't think people in NLP care, one question that they always ask is kind of the art of chemistry. Can you generate many possible improvements? Because at the end, only few of them will work, so you really want to be creative with your outputs. So our idea was, maybe we can make our model to be interestingly creative. And I'm not talking about interestingly creative by just taking, top K molecules based on the probability, because they will be very similar to each other. So we really want to generate the right diversity. And the way it has been done, we provided the model with the pairs of molecules, as I told you, all automatically constructed from the high throughput screening outputs. And now the molecule learns this whole translation process. And the only kind of innovative piece was, how can we generate the right diversity? And what we've done, because our input data does show interesting diversity, so we actually added, a latent code Z, which you concatenate to your hidden representation, and depending on its value, you would generate different molecules. And you can estimate the Z and kind of create different diversions from your original hit point. So at any rate, that's what we've been doing. In the paper, I think this is a clear paper. We, tested it on many, many different data sets, both in terms of accuracy and diversity. It seems to be working better than others. And now we are working with Amgen on utilizing these techniques in the development of CNS drugs, central nervous system drugs. There was somebody who wrote a paper about what are the properties from Pfizer, what are the properties of the central nervous system drugs that were successful, so we kind of know what kind of criteria needs to be optimized in our molecules to generate something useful. So that's pretty much what I wanted to tell you. And I would say, to conclude my talk, I would say that I think this area is interesting, not only because there is a lot of algorithmic work that needs to be done, and there are a lot of transfer questions and other things. I think that we really have a chance to change how drugs are designed. And if you look at all these diseases that, I'm sure affected either directly or indirectly many people in this audience, I believe that, if we take all our energy and put it here directly or indirectly, we can make a difference. Thank you.
So thanks for the fantastic talk. We have time for probably, say, 2 questions. So if anyone has questions.
So what I gathered from your talk is there was a lot of trial and error going on with choosing the right representation for the molecules and choosing you were also talking about choosing loss and I guess even optimization techniques. So is there any more high-level techniques that go, I guess, beyond trial and error that are insights that you gotten through, like how to choose or how to intelligently select, or if I'm making any sense?
Thank you. This is a great question. So I would say that what we've seen that by designing customized models that obviously maybe build on more standard architectures, but really understanding what are you trying to model, we've seen that this overall yields better performance and it enables us to generalize better. There are some places where we've done it successfully when we understand the chemical properties and we could inject this knowledge into the models. There are places where I think our understanding is still behind and lacking, and there is a place to do more improvement. But besides, so there are two pieces. One is, how do you, which laws do we select and what is the right architecture? There is also a bigger and fundamental question is how can you take what was creating in physics, in computational chemistry, there is a lot of knowledge out there, and the top performing system on a variety of tasks are not using this data. We don't know how to incorporate it. It's not for the lack of trying. And I'm still hopeful that we will find a way to do it smartly.
Yeah, so it's sort of continuation of the question. You talked about representation going beyond graphs and modeling the physics. We heard about the word vector and related representations in the morning also, and taking dot products. I'm wondering how well we know about the coordinate system or the representation so that we can say that this is a dot product or cross product, because as a physicist, if I want to model something, I'd like to know what is the coordinate space that I'm working in. If I'm trying to model the flow of water in a pipe, I would use cylindrical geometry. Using a Cartesian geometry would be interesting, but not very practical. So is there an effort to put all this in a more formal coordinate system or a framework so that what is done for one system can be translated or used in another system?
So I think this is again a great question, and it particularly arises, it's very clear when it becomes a point is when you're talking about the 3D representation and how do you capture angles and other things. So today the field is at the point that everybody kind of comes with their homegrown model and compares in a certain task and say I'm doing better, that's why my representation is better. But I don't think that we're mature enough to make some generalization over these individual efforts and, provide deeper insight. I don't think we're at this point. I mean, and I should say that if you look at NIPS and the ICML, the papers in this area start kind of cropping up in the last 3 years. Before that, this area was pretty much non-existent for that community. So there is a lot of work to be done. Can I go now?
Thanks.